Okay, thanks everybody for sticking through a full day of CXL talks. I've got kind of a review of CXL 3.0, some of actually which was touched on by my colleague Vince earlier. And probably a lot of this is review for those of you that have been kind of sitting in all day. I figured I'd go off script a little bit just because a lot of this is just going to be review. If you don't mind participating with me for a moment, how many of you in the audience are working with CXL today? Okay, I'd say about 50%. And how many of you would you say are investigating CXL for potential stuff? Okay, great. Okay, well, welcome to my talk, and for those of you investigating CXL, hop on board. There's lots of opportunity. For those of you already working in CXL, glad to have you on the team. Fantastic. My name is Danny Moore. I'm a senior manager at Rambus. I focused on product management and strategy at Rambus, and we've got a new business unit at Rambus that is primarily focused on CXL. I've been working in the industry for over 20 years, mostly focused historically on PCIe switching and PCIe switch fabrics. And then was lucky enough to be involved in the CXL consortium kind of from the early days in 2019 to present. So what we're going to be talking about today is CXL 3.0, which was released in August, some novel device types, some of the new capabilities that are coming in 3.0, and then obviously the expansion of the interconnect itself beyond what was previously defined into the kind of the fabric space. So I'll give you a quick overview of 3.0, and then I get into the new device types themselves, the multi-headed device, which we talked about previously, and kind of a comparison on a concept called memory pooling, which you've probably heard 50 times today, with respect to what we had in 2.0 and what we're bringing in 3.0 to make it a little bit more composable, a little bit more interesting. The dynamic capacity devices, which is really a capability that's added in the 3.0 specification, which adds like a new layer of composability to what we had in 2.0. And then of course, fabrics, right? 3.0, one of the primary components of 3.0 is this concept of fabrics as we move beyond kind of what we're normally historically seeing in PCIe type topologies to a pure fabric topology, where you're no longer restricted to kind of a hierarchy-based communication direction. Okay, so 3.0, we've got a litany of great new stuff that came in 3.0. One being the fabric, which I've alluded to already, which is really enabled by a port-based routing mechanism that we implemented in 3.0. And what that, at a high level, what that really means is, in a historical PCIe type up-down topology or hierarchy-based topology, transactions were routed based on their header type down towards their target destination, and responses were routed back up. With a port-based routing mechanism, you're no longer constrained by that hierarchy. Now you can tag, you can say, I just want to hit this destination port, and I just came from this source port. And with that type of new mechanism inside the flit header itself, we're able to route things horizontally, per se. So now we're no longer constrained to switches beneath other switches. Now we can have switches in a wide array of different configurations, and I'll be talking about that a little bit later. Improvements to memory pooling. Like I said, we've got the multi-headed device now, and for me, when I think about multi-headed anything, it's a real simple story for composability, right? We have a resource, and it connects to multiple things. Those multiple things can now share that resource. And then we made some additions to memory pooling, which is the concept of memory sharing, right? So previously, memory pooling was restricted to, we have a large pool, this piece is connected to this head, this piece is connected to this head. Now with memory sharing, we can actually say, well, this piece can actually be shared by both heads. And the symmetric coherency is really one of the mechanisms that really enables that. So now the way that you can maintain coherency between these three pieces is to have a symmetric coherency hardware-based mechanism where the device itself can now invalidate a host cache, whereas before the host would invalidate their caches solely, but now with the symmetric coherency, we can invalidate the host directly. And then with that symmetric coherency, we also add some new capabilities such as peer-to-peer communication, which once again, now we're no longer restricted to first communicate a transaction to a host, but now we can actually go from device to device. And then all of this kind of comes in the same familiar backward compatibility that we're used to seeing in PCIe, for example. So here we have a bit of a chronological layout of the PCIe specifications. 1.1 really bringing disaggregated memory to the marketplace in 2019. 2.0 we've stacked on things like MLDs and memory pooling. The concept of CXL switches was added. And then in 3.0, which we just released in August, kind of bringing that level of composability to the next level. And the addition of a 256-byte FLIT, which really help bring some of these additional features along the bottom, the symmetric coherency, the back and validate that I mentioned, memory sharing, and of course the fabric capabilities. And in 3.0, we also sit on PCIe Gen 6 electricals, so we get the same kind of link resilience that we're used to in PCIe, and with 6.0 and PAM4, we get a FEC to help kind of drive low bit error rates across the link itself. Okay, let's talk quickly about the multi-headed device here. So as I mentioned, pooling was really brought out in CXL 2.0. And it was really spec defined and enabled by CXL switches. And on the left here, we can see a composable memory pooling solution where multi-logical devices, that's these devices along the bottom, can be programmed to expose different regions of memory to different hosts. And then in 3.0, we bring the concept of the multi-headed device. So with the multi-headed device, what we see is now the switch is really embedded, or a switching fabric is really embedded within the memory controller itself. And so on the CXL pooling memory controller, what we have is multiple heads, and then the media controller, whether it's DDR or some sort of emerging memory, sits within the controller itself. And so, visually, it's quite simple to see some of the benefits of the multi-headed device in 3.0. Here we, on the left, with the switch-enabled pooling, we get potentially some larger expansion into even potentially larger pools of memory. But one of the restrictions is you need to traverse two CXL links. One at the top of the switch and one at the bottom of the switch, which then leads to a controller, which then has the media controller in it itself. Whereas on the multi-headed device, we only need to traverse a single CXL link. And so you lose some expansion or composability capability in the multi-headed, but I think what we're seeing is that really this is the kind of the sweet spot for composability, at least right now, where we get a higher performant memory pool with a lower overall latency compared to a CXL switch. Any questions? No? Okay. Feel free to stop me. I don't know. I imagine you guys are running out of juice just like I am. So if you have a question, just yell it out. It's no problem at all. Okay, so two types of multi-headed devices. There's the multi-headed single logical device, or MH-SLD, multi-headed multiple logical devices, or MH-MLD. And really the difference between the two is how resources are presented to the heads or presented to the hosts. An MH-SLD presents single logical devices to the host, and an MH-MLD presents multiple logical devices to the host. With the MH-SLD, we have a one-to-one mapping of LDs to hosts, and with an MH-MLD, we have up to 16 logical devices. But the MH-MLD, so remember the MLD concept really came in 2.0, and so the MH-MLD concept kind of was an adder into 3.0, so we could maintain some of the MLD composability that we are used to and that we had the frameworks built for already. But for the MLD functionality in the MH-MLD, you still require a switch. So here's logical abstraction. These diagrams are directly from the specification, so you can download the specification yourself. It is public, and it's a great read for late nights and long weekends. So on the left, so between the two pictures, we can see we're still accessing the same pool of memory, but how the LDs are bound to the different heads is really the differentiation between the MH-SLD and the MH-MLD. Okay, so let's move on to the dynamic capacity to device capability. This is a really novel and interesting capability that came in 3.0, and it's kind of a simplistic solution, but obviously there's levels of complexity to it. So really, what is the problem that the DCD framework is trying to solve? So prior to the definition of the DCD framework, we used HDM decoders to map host physical address space to device physical address space. So you have a CXL Type 3 memory device. It has some media attached to it. There's a physical address space associated with that. I have 1 terabyte of memory or 500 gigabytes of memory. And that needs to be mapped into host memory. So these HDM decoders are simply programmed by the host to map the host memory space into the device physical memory space, so it can access the media. So this works really great, and with a multi-headed device, you have multiple HDM decoders, and each decoder can expose different quantities of media to the hosts, and each host can independently program its own HDM decoder to map the underlying media addresses. But the problem with this sort of configuration, in looking at this example, I show 2 hosts mapping a 1 or 2 terabytes of physical media, each one accessing 1 terabyte. But we want composability, so let's say host 0 is utilizing all of its memory and would like more, and host 1 is underutilizing its memory and doesn't need to have everything. So no problem. You can just simply reprogram your HDM decoders. The issue is that in order for the host to comprehend that new memory range into its fully already mapped system memory, you're quite likely going to need to stop or QoS any traffic and potentially even reset the host domain. And really, that is the problem that the DCD capability is solving. So how does it solve it? So what the DCD capability says is, well, why are we only mapping portions of our underlying media? Let's map the entire range of physical media to each host, right? And so the DCD framework is really a memory device that implements that command set to program those extent lists and those HDM decoders, and so now we can see that each host actually has mapped the entire physical address space now on the device. Now this presents a new problem, and the new problem is, well, how do you prevent host 0? Before we each had them some assigned memory ranges, and they could operate happily touching their own memory and not touching each other's memory. Well, now we've mapped the entire range, so how do we prevent host 1 from writing and reading host 0's memory and host 0 from writing and reading host 1's memory? And so the other level of the DCD capability is this concept of the extent list. So the extent list is managed by the Fabric Manager, and it's programmed and queried by the DCD command set itself. And what the extent list does is it divides the physical address into separate regions, 1 to 8 separate regions, and each one of those regions is then subdivided down into fixed size blocks. And so this extent list keeps a finer grain, you can think of it as a database of which memory is assigned to which host. So even though the host has mapped in the entire range of physical media, the extent list actually maintains a level of restriction there. And that extent list is communicated to the host. So the host is aware of what memory regions within its entire mapped range that it can actually access. But then also the extent list itself is actually maintained inside the memory controller as well. So if you have a rogue host or a rogue element, accelerator, whatever, that has mapped in this entire range, and it attempts to access something outside of its allotted extent list, then the memory controller itself can just treat that as an HDM decoder miss and handle it quite smoothly. It can say, no, you're not allowed to talk to that memory address. Okay, and that's the DCD framework. Any questions? Yes. Yeah. If you implement security, you can implement it so that the transactions are blocked by the DCD itself and the controller, and then also if you've implemented security in terms of secure boot, et cetera. Yeah. Fabrics. So here's kind of a hypothetical diagram of what a fabric could look like. Here we see, like I said, we're no longer subjected to the hierarchy-based switching topologies that we're used to seeing. And here we're no longer restricted to hosts kind of at the top of the hierarchy and devices at the bottom of the hierarchy. And this diagram is also good because what you can extract from this is that there's actually multiple paths from different sources to different destinations, and that's also one of the advantages of fabric-based switching. And then we also actually created with 3.0 the concept of some fabric-aware devices like the GFAM device. So now devices not only need to respond, just here's a response and it doesn't need any routing, but now they can respond with what was a source ID in the request itself. And so they can append a destination ID to their response, and then the fabric can be programmed in such a way to recognize that destination ID means over here. So once again, these are some diagrams right out of the specification. You can access them on your own. But really what we tried to achieve in 3.0 was highly configurable, right? And what you see on the left here, you'll see the acronym HBR and PBR. So PBR is a port-based routing switch or a fabric switch. And then the HBR is a hierarchy-based routing switch. I also think of it as host-based, but hierarchy-based routing switch. So what you can see is you can mix and match, ostensively, right? You're not restricted. You can connect kind of normal hierarchy-based fan-out style switches to fabric-based switches. And so you can begin to conceptualize, like, you know, a wide array of potential switching topologies. And then on the right, which we kind of highlighted in the diagram on the previous slide, you can see once again there's the potential for some circular conflicts, right, where there's multiple paths to get to the same destination, and all of that can be managed within the switches themselves and their routing tables, etc. So yeah, so we expand from kind of the normal switch hierarchies, and with the concept of fabrics, we now go beyond kind of node level switch hierarchies to kind of rack level and even beyond the rack interconnects. And all of this is really enabled by the PBR switching framework. As I mentioned, the transactions are routed by a source and destination ID as opposed to kind of an address, right? The FLIT was provisioned with a 12-bit source and destination port ID. So conceptually, that's 4,000 devices, right? That's what we wrote into the spec. And so, you know, you can theoretically put together the concept of, you know, 2,000 hosts and 2,000 devices all talking to each other with enormous pools of memory, enormous pools of compute, all composable, and every device can talk to every device. And the concept of the global fabric attached memory device, once again, this is a slight change to what we have today with kind of our normal type 3 devices, where responses are just traversed kind of up the hierarchy directly back to the host. Here, the GFAM device will actually append its response with a new destination ID, which was simply a copy of the source ID on the incoming request. Yeah, please. 4K is pretty big. I think long before we get to 4K, we'll probably be putting provisions into the specification for more. But at this moment, I think, you know, let's get to 1K, and then we might start talking about adding some more provision. I suspect there's you know, I'm not super familiar, but I suspect there's provisioning within the FLIT headers to potentially expand on that if needed. But I also think that that's probably a long ways away. So you're already ahead of me. Okay, and then yeah, the call to action. You know, I think it's fantastic. We've had at FMS and at OCP here just kind of like so much engagement on CXL. I encourage those of you looking at CXL, if you're not working on it already, feel free to come say hi, talk to me. You can download the specifications. There's white papers, there's videos, there's tutorials. You can get involved in the CXL consortium, and come and participate OCP as well. Okay, thank you very much.